Okay, so here we got another magnetic field slash force per unit length question. Okay, so we have three long parallel wires that are arranged as shown in the figure right here. Okay, and then determine the force per unit length acting on the wire. Okay. So before we start anything, we're going to label our axis. We're going to create an axis. Okay, so it's going to be this right here, and this right here. It's going to be x, y, therefore z is going to be up and down. Okay. Okay, force per unit length. Well, force can be described by this equation here. Okay. So the main thing here is to find the magnetic field acting on a wire carrying I3. Okay. So we know that I1 equals I2, but they're both in an opposite direction. So in magnitude, it's equal in magnitude. However, I1 goes into negative z direction, and I2 is in the positive z direction. Okay, so let's draw this on here. Okay, so I1 and I3. Let's do it by this blue marker here. Okay, so this distance here, I'm going to call R1. This is the distance between current I1 and current I3. Okay. Therefore, using BS's law and using our right-hand rule, we know that the magnetic field at I3 on the current I3 due to the current I1 is going to go this way here. So let's call this B1. Now for I2, this distance right here, so let's call this R2. Okay. And then we also, by BS's law, we know that the direction of the magnetic field acting on the wire carrying I3 due to I2 is going to go this way here. Therefore, the resultant vector is going to go in the negative x direction. So let's call this Bx. Okay. Okay, let's look at the magnetic field acting on the wire carrying I3 due to I1. Okay. Okay, so these are three long, so we could use Ampere's law. Should call it R1. Let's call this B. This small b is going to be the unit vector in the direction of B1. So let's put direction here. So we won't get confused. So the direction of B1 is going to be mu naught I1 over 2 pi R1 in the direction of small b. And again, small b, this is unit vector in direction of B1 we have in the diagram as B1, so let's have it as B1. Okay. So this B1 is going to be this right here. However, since we know that Bx is along this axis here, it's going to be in the negative x-axis. Let's find the x component of the magnetic field acting on I3, on the wire carrying I3 due to I1. Therefore, B1x equals times this angle here. Okay, so that angle there, so we know okay, so we know that tangent of theta equals 2 meters over 2 meters, therefore equal to 1, so we know that angle is going to be 45 degrees. It's going to be 45 degrees. Okay. For B1x equals 5 mu naught. Let's do this. Let's substitute that I1 in. I1 is 10 amperes or 2 pi R1. Therefore, B1x equals 2 mu naught 5 over 4 pi. And notice that I didn't put the vectors on top of here. Therefore, I don't need to label it. Put this as the unit vector, the unit vector there. Okay. Actually, let's make it easier. Let's put the direction. Therefore, it's gonna be negative x hat. So if I put the cosine 40 here, degrees, therefore this equals to negative x hat. Okay, let's do this all over this part again. So now that we put the direction, it's going to be negative x hat mu I1, which is 10 amperes over 2 pi R1. Okay, let's find R1. So R1 is going to equal to the square root of 2 squared plus 2 squared, which is going to give us square root of 8. Okay. So substitute that in. And cosine of 45. Therefore, this equals negative x hat 5 mu naught 4 pi. Okay, so that's the magnetic field acting on the wire carrying I3 due to I1. Now let's find the magnetic field acting on the wire I3 due to I2. Okay. And also we want to, so the magnetic field at B2, since it's the same distance and the same magnitude as the magnetic field due to I1, we can say that remember, I'm not putting an x there, so it's going to be B2 mu naught I2 over 2 pi R2. This equals to mu naught times 10 amperes over 2 pi times the square root of 8. Notice that the magnitudes are the same. Okay, again, we're trying to find the x direction because the resultant vector is going to be in the x direction. That way, we want to find the x component of B2. Now, we are dealing with B2. Oh, we are dealing with a vector, so this has to be B2 hat. Let's call this one B1, B2. B2 is going to be the unit vector in the direction of B2, okay? Now let's find the x component. So it's going to be negative x hat. Times cosine 45 degrees. Same angle. Therefore, B2x is going to equal negative x direction 5 u naught over 4 pi. Okay, now what we want to know the resultant vector in this, the resultant vector, which is going to be bx. Okay, so we know bx negative x direction times b1x plus b2x, just the magnitude. Okay, therefore, bx equals negative x hat times, let's write it over here. So bx equals negative x hat times 5 mu naught over 2 pi. Now, but that's not the answer. We're trying to find the force per unit length. Using this equation here that we mentioned at the beginning, we have the force equals IL cross B. It's cross B, but in this case we're going to call it BX, okay? So this is going to be I3, okay? So the force, yeah. You know what? Look, let's write the general formula and then we'll move on. Yeah. Okay. So we want to know the force per unit length acting on wire carrying I3. So we know the magnetic field at I3 is described by this Bx here, and we know that the current, we know that the wire carrying I3 is in a negative z direction. Okay. So we write this as oh, yeah, 10 amperes cross. Yeah, to make math look easier, is I3L cross BX. Okay. Therefore, this is going to equal I3L times BX and then cross the direction. So we know that the direction of I3 on the wire here is going to be the negative z direction, and cross And we already concluded that Bx is in the negative x direction. Okay, now we have this formula here. We're trying to know the force per unit length, so we could divide this L over. And this equals negative z cross negative x is going to give us positive y using our right-hand rule. Okay. Now it's going to be I3, which is 10 amperes, times this value here of Bx, the magnitude of Bx. Okay, let's move this over here to this side. The force per unit length equals positive y hat of 25 mu naught over pi. This equals to 25 plus y hat time of 25 times 4 pi times 10 to the negative 7. That's the permeability constant, which is described as mu naught over pi. Therefore, we get force per unit length is in the y direction of 10 to the negative 5 newtons per meters. That's the answer right there. Okay. Thank you.